and a little bit about myself first. So I grew up in Germany, kind of got enough of the Germans, moved up to Scotland, a bit cold there, moved to London, still a bit cold there, and then after a lot of data analytics, everything pointed towards Sacramento. It's a nice, cozy, warm place to spend the summer. So yeah, I spend my time now mostly in Sacramento, but still quite a bit in London, where I have a small company. Our company is Evergreen Innovations, and I'll give a brief introduction to that in a moment. But most of my background work is in really any piece of software that somehow interfaces to some form of hardware. And there's quite a lot of different examples for that. But maybe just a bit more about kind of my own journey, how I've gotten into where I work now. So I used to be in academia, was a professor for a few years at Imperial College, and I ran a master program there called Sustainable Energy Futures, and really ever since I've been in energy systems, so anything to do with power generation, offshore wind generation, battery storage, so really anything around the energy system. In academia, I generally found I couldn't really push on industrial solutions, so I set up Evergreen Innovations, kind of as a hope I could act like an incubator type company, but much more on the technical level. So most incubators are very focused on the managerial business development side. What we do as a company is we are trying to push startups through those first few difficult years when they don't have all the technical skills in-house and need some guys to help on things like this. So we do control systems, back-end engine work, cloud computing, data intelligence, kind of the whole range, but generally start on the very left with something that's hardware related. So I'll give you an example. Our biggest project at the moment is a very large industrial battery that would fill this room 3 times over. It's the biggest battery, or probably the second biggest battery in Europe, and it sits there on the grid to provide some stability to the grid when you have a lot of what's called intermittency. So you have solar coming in, you have wind coming in, but it's not very predictable. It's predictable to some extent, but not entirely predictable. So you need some storage in between, and that's what we work on a lot, providing software and also hardware electronic services to battery storage companies mostly. So today's talk was really motivated by, I guess, an observation that when we look at AI, we think of neural networks as kind of being the solution. We just kind of dump a load of data in and something nice comes out in the end. And that can work sometimes, but sometimes it doesn't work, particularly when you look at time series data. For example, in our case, we work a lot with electricity market data, so price data, and we need to predict, the price is going to be exactly, or reasonably exactly this price now, so we can buy it cheaply, and then maybe we need to predict a couple of hours in advance to know when we can sell at maximum profit against the electricity we've been storing. That would be an example of time series. Another example would be medical data, EEG data, for example, and there's a bit on this in here in a moment. And what made me think about this whole log business here is that very often we just kind of throw data into a neural network and we don't think too much about it, because that's kind of the point of a neural network. You don't have to think about it. The neural network should be doing the job for you. But sometimes you can just drown the neural network with so much bad data that just garbage will come out the other end. So thinking about different ways we can deal with signals is important, and just to give you an example of that, I wanted to talk a little bit about why in electric engineering in particular we often use logarithmic scale. This is just one example here where, let's say you have a sine wave, this is a 1 Hz sine wave, a 20 Hz sine wave, and a 50 Hz sine wave. It's probably hard to see on the axis, but this scale here is 1, this scale is 1 over 100, so 0.01 here, this is 1 over 1000. So when you then look at the sum of those, so this signal here is just that, that's that, you can't actually see those two, right? Because they're so much smaller, they're just kind of sitting on top here somewhere. But you don't see them because they are so much smaller than that fundamental signal. And that happens very often. You might have the heartbeat signal of the patient, for example, and that might overshadow lots of other things that might be going on in the brain or whatever else it might be. So if you now take a Fourier Transform of that, what you can see is this one spike here at 1 Hz, this is the frequency axis now, is clearly visible at 1, and then this 20 Hz component, do you see that little bit here? And then the 50 Hz, that should be somewhere here, but you just don't see it, because it's so much smaller in magnitude that you won't see it. Now if you take exactly the same data, but put on a log scale, now you can actually see all three signals. So it's exactly the same data. There's no difference between this plot and that plot. All I've changed here is the axis. So the left axis, the y-axis, here is linear, and here's logarithmic. And now you can see the 1 Hz component tends to 0 to 1, and then the 20 Hz component, if you look here, this is already 10 to the minus 5, this is 10 to the minus 15. So what you see here is what you would call epsilon. So that's your residual error in an FFT, something like 10 to the minus 16. And then you can also see the 50 Hz component. And then you take that maybe one step further, and you also put the x-axis on a log scale. And what that does, it kind of tends to put different orders of magnitude and frequency closer together. So you can see something that happens at one frequency and then at a more removed frequency closer. So again, just changing the axis on this and makes quite a difference. Right. How can we now apply this to something useful? So we've recently started playing around with a data set that's on Kaggle. It's EEGs of dogs and also humans. And the typical signal would look like this. Kind of an EEG signal. This is channel 1. This particular data set has 16 electrodes around the head. And you basically measure the EEG signal for a 10-minute period, and then you have, I think it's 50 for each dog, and there's I think something like 5 different dogs and then 2 different humans. Now the problem with that data, first of all, it looks very noisy. Can't really see a clear trend. It's really a lot of data for one data set. So if you try to feed this into a neural network with 4 million data points, you'd be training your network forever. So we've been, in this example, just trying to think a little bit, what can we do with signal processing before we put it into a neural network to get a bit more out of it. So the first thing we did is, okay, take a Fourier Transform of it, put it on a log scale, see what happens, and you can kind of see the most important stuff is going on here, and there's something else going on here, but it's still a very, very bad signal. You can't really see what's going on. And putting this into a neural network, now in the frequency domain rather than the time domain, might help you a little bit, but probably still doesn't really lead anywhere. And what I'm trying to explain now, you don't have to understand necessarily the detail of how this is done, but there's lots more techniques in signal processing which you can apply. This one in particular is called the Welch parallelogram. And what it does is you split your data into segments, and then you run what's called a window over it. This particular one is called a Hamming window. So rather than just taking a straight FFT, you take the edges of the observation and you smooth them at the sides. You then run the window over that in several instances. You do some overlapping. So this is kind of a very standard technique in electrical. It's called the Welch parallelogram, the whole process together. And you can see what you can achieve. You can kind of get from this mess into something that has now a very clear primary trend. But you can also start seeing the secondary signal coming up here. And there might be a little third one here. And what we can now do is we can separate that into little elements. So we take maybe this data, then we take that data, and each of those maybe just 1 Hz intervals. So each of those 1 Hz intervals would then become the input to a network. So what we're playing around with at the moment is so we have 150 features because we have 150 Hz bandwidth, and we take 1 Hz intervals. Should I try this before maybe? Let me try this before. Okay. So So what we're trying at the moment is then to take the data from the 16 electrodes times 150 features, so we get something like 800 or so observations, put them into what's called Siamese convolutional neural networks, and put a fully connected layer, and this is what we're still working on to try. Really what this particular data set is to predict epileptic seizures. So some of this data is from a non-seizure event, other data is from a seizure event, and the competition here, this is close about 4 years ago, but it's a nice data set to try new things on. What you're really trying to do is predict that the epileptic event is going to happen at some stage in the future before it happens. That's kind of the point. So to see trends in the data, and as I said, if you start feeding something like this into your neural networks, I think it's a lot harder than actually working with on the data first, and then giving the neural networks a slightly more informed version of the data. Which isn't really what neural networks are for. You kind of think that they will just put things in and things will happen. But very often, doing a lot of signal processing on it, and this I think is a really good example. We haven't quite gotten the output yet, but I think it looks pretty good so far, is hopefully worth doing. And as another example, if we use the raw data, we would have 4 million data points per set for each 10-minute interval, and then so many 10-minute intervals. So we'd have, something like 50 million data points to train the model on, which is just basically you'd have so many parameters in your neural network, you just flood the neural network. Whereas here we have 850, so we've condensed it down to what is actually the important data, and now we're trying to build a good neural network to take that slightly processed data. Last one for closing, maybe just another way of looking at the log scale. Anyone's ever tried to make any filters for some of the analysis? Again, if you understand log scale and what it does, then it can help. So this, for example, is a first order low-pass filter, this is a second order low-pass filter, and just from the slope of this line on the log scale, you can very quickly see which one it is, but never mind that for now. Right, any questions? Yeah.
How did you narrow down from all those parameters to was it 16 parameters that you said?
It's 16 electrodes, so that we know. It's a fixed number, so it's a fixed number of electrodes. We don't have a choice there. But in terms of narrowing it down, you have a choice still. What we decided is we have a frequency band from 0 to 150 hertz. Let's just try to feed the neural network effectively the average of 1 hertz frequency bands. We could have chosen the average of half a hertz, or 1 of a hertz, or 10 hertz. So there's still flexibility in how many data points you can generate by taking, say, averages over these frequency bands. So this here, for example, would now be the 150 points that comes from this particular electrode in this particular 10-minute time interval. And then you'd have a similar one for the next 10-minute time interval. And then hopefully, as you go through time, you start seeing the event that led to the seizure.
So I've only seen convolutional neural networks discussed in articles on image recognition.
Yeah.
What is it that you feed into the network derived from this?
The frequency information, so the 1 hertz information so basically each of those points. So say this point, this point, this point, this point, that's the inputs.
Well, neural nets are pretty wide, right? I mean, they'll take more than just images, so they have like modules which can include data. So
yeah, I mean, you could. Yeah, I know they're most used for data processing. We have there's one pretty good paper by Stanford that we found that use convolutional neural networks on something fairly similar, and that's partially why we've been going in that direction. But we could do something slightly different. It doesn't have to be convolutional neural network.
I'm not very knowledgeable in these areas, but like images are, can be represented as like a matrix. I guess what's the structure of this case?
Well, convolution as such is just finding the correlation between one thing and another thing. So convolution is just a mathematical operation that's being broken down into a neural network. And really all a convolution generally does is you take one thing, you take another thing, and you slide them over one another. And generally, if there's a good correlation between them, you'll see a peak somewhere in that convolution. So if there's some correlation in the data like these peaks, and then you slide maybe for instance, you do an autocorrelation on this, so it with itself, then that peak here would present a particular feature in that signal, and that one would too. And what we're really looking for is the features that led to the event. And we don't know what it is. We don't know if it's that peak or maybe something that happens down here or this one. We just don't know. But we hope that whichever it is, through the convolutional network, the feature should be detected. And this is maybe a bit like in an image, like detecting an edge or detecting maybe a spatial, whatever, rectangle or something. Just detecting that one feature, like this one spike here or that one spike there in the data. But we don't know yet. That's still work in progress.
Yes.
Yeah.
So your assumption is like if we find the relation between neighboring points, we can actually conclude if there is a seizure or not.
Yeah, so for example, the relation between neighboring points could be that from here to here we have a very sharp increase in the power at that frequency, and maybe if that frequency is what actually led to the event, or, you know, because I don't know, like the data I've shown here isn't necessarily the data that led to the event, right? There might be somewhere in all that data an image similar to that that has a spike here. We don't know, right? That's the beauty of it. We don't have to know and explore the data. And hopefully the network will tell us at the end. So I know that groups that have done this without kind of image, without processing like this have gotten to about 70% accuracy on the predictions.
Mm-hmm.
So you can definitely get quite good with this, and we're trying to push it hopefully into the 90%. That's kind of why we're putting a bit more effort in. Yeah?
And I'm still not sure I understand exactly what you did. So you've got 10 minutes of electric readings from doohickeys on people's brains and dogs' brains, right?
Yep. Like this. That's the actual signal. But 10 minutes of it.
Okay, and then, so I'm confused. It looks like you drop time as a variable altogether, and you just start counting like frequencies of how strong the electric signal is this
Yeah,
just taken
so
up?
you take a Fourier Transform on it, on the signal, say FFT in this particular case.
Okay.
And then we do something slightly in addition to that, which is called this Welsh parallelogram, which is a process that effectively enhances the output from that. So these, if you ever want to read up on these have been developed primarily, or like all crazy things, in the context of military. So doing submarine signature detection, that's where most of this work comes from. Like, you know, the United States wants to know where the Russian submarine is, and then you go listen behind all the whale stuff, right? Like, where are they? And there's a lot of noise, so trying to find something like this in something like this is really what this parallelogram does. So it's trying to already help detecting some of the features of the signals and not paying attention to all the noise around it. Okay?
I was also trying to understand that. So let's say if you want to predict the seizure of a patient,
Yeah.
then this is supposed to be real time. So you need 10 minutes of data, and based on that, every 10 minutes you can predict.
Yeah, I don't know yet. It's that's something we can maybe break down a bit if we could do it on a 1 minute interval, on a sliding window, for example. 10 minutes is quite long, I agree. Yeah, because you may not have that data available right now.
I'm still quite new to this field, but I was thinking like if the data is dependent on neighboring points,
Yeah.
why not recurrent neural networks?
We could try that too. Yeah. And I am by no means an expert in medical data. Okay. The main reason I look at medical data is because all the data I generally working with my clients is commercially sensitive to the client, so I can't work on it. So I need to find something else that's not under contract and confidentiality agreement.
So aside from that, is there any reason why you would be interested in the neural activity of a dog?
It's another time series for me. No more, no less than that. Another time series with interesting features on it. And yeah. That's it. And there's lots of medical data, there's lots out there. There's much more medical data out there.
I was just wondering if there was like anything that they were able to discover, by studying the brain activity of the dog.
There's also human data as well.
Okay.
Yeah, so that same data set, so the data set has dog training data and then also 2 humans. The reason most people start on the dog data is because at a much lower sample rate and the data volumes. So one data set, what is one dog is about 5 gigabytes, and that's the 16 electrode. One human is about 17 gigabytes. And putting that through a neural network is a lot of data.
Why is it larger for a human?
It's higher frequency. So the signal is recorded at a higher sample rate. And I don't know exactly why, but probably maybe maybe it's just empty. Maybe we have to look for longer. Yeah, I don't know. But again, I'm not in the medical field. I can't tell you that.
Okay, let's do one more question
Okay.
and then we'll.
We're going to Walter.
Was the assumption that all of these subjects eventually had a seizure?
So you have, the data set will tell you. So the data set actually gives you, just like most training data sets for neural networks, gives you, it's actually the file name of this particular data set. So the file name of any set you pick up here, like this is doc2 intercritical, that file name will tell you whether it was an event that led to seizure or it wasn't an event that led. So you know from the file name. So the event will be somewhere in the data, in some of the data sets, and you know that. Okay? Great, thank you.